This is a summary of what you have learned in Chapter 1 and Chapter 2. We know a computer is a device that is capable of processing, storing, and communicating information. Designing, understanding, and implementation of such a device is the scope of the computer architecture. Now, there are different types of computers. They don't need to be electronic. However, our scope is limited to digital electronic computers. There are several key inventions in this path. For example, the programmable machines and transistors are very important inventions for the development of the modern computer. And scientists like Alan Turing and John von Neumann had played key roles to designing the modern day computers. To process information, first they need to be represented inside the computer. In electronic computers, voltages are used to represent the information. If a continuous voltage signal is used, it is called an analog computer. On the other hand, if if the discrete voltage levels are used, it is called a digital computer. As you had learned on the previous lecture, there are many advantages of using digital signals. Modern day computers has two discrete levels or binary levels. So everything you see in the computer, like characters, images, or numbers, are represented using ones and zeros inside the computer. The first standard mapping of characters to binary patterns was the ASCII standard, or the American Standard Code for Information Interchange. However, it could not represent all the characters of other languages. It had very limited number of characters. Therefore, modern day computers use Unicode to support multiple languages. When it comes to representing numbers, there are different ways to where you can use different methods you can use to represent numbers. If your number is a positive integer, or in short an unsigned int, the easiest way is to do a conversion as shown in the figure. I'm sure you have covered something similar during your physics course at your advanced levels. You take the number and continuously divide it by 2 until you get to a final result of 1. And each time you make a division, you write the remainder of that division. And then you collect or append all the remainder values and get the binary number. If your number has a fractional part, then you multiply the fractional part by 2 and write the integer component or the carryout component of the number. That will create the fractional part in binary representation. But not all numbers can be represented using finite number of bits. Some numbers will have a continuous trail of repeating bits. In practicality, you have only a finite number of storing capacities. That means after a certain number of bits, you have to neglect the rest of the trailing bits. Error caused by such a truncation is known as the truncation error. So here look at how to represent positive numbers. Now let's look at how to represent negative numbers. There are three common methods that are used to represent negative numbers. First is the sign and magnitude method. If the number you want to convert is a positive number, you just follow the unsigned number conversion method, but you have to make sure you have at least one leading zero. If you don't have a leading zero, you need to add a zero to the front. If it is a negative number you want to represent, first take the unsigned format of the positive number, then add a 1 to the front. So make sure you have a leading 1 at the front. In the ones complement, for the positive numbers, you do the same as the sign and magnitude method, making sure that you have a leading 0. If it is a negative number, you do the sign and magnitude, if it's a negative number, you do the unsigned integer unsigned conversion and make sure you have a leading 0. Then you flip all the bits of that number. If you need any extra bits to the beginning, you can add leading ones. Two's complement is very similar to one's complement. If it is a positive number, you follow the one's complement method. If it's a negative number, you add 1 to that number and then take the one's complement of the new number. There is a maximum and a minimum value that can be represented using a given number of bits. So if you try to fit a larger number than what is able to fit in that space, you will get an overflow error. This can happen when you try to add numbers or to multiply numbers. Your starting numbers may be able to fit it 4 bits, but your result may need 5 bits to store. So it is important to know the limits of the different bit size and different number formats. We may also need to convert binary to decimal. If your binary number has a leading 0, then it is very easy. It is a positive number and you can multiply each bit by its binary point value and add them together. You can see an example in the image. If it is a negative number, if it has a leading 1, that means it can be a negative number, and therefore we need to know which format is used to convert that binary number. If it is an unsigned number, we can simply add a leading 0 and treat it like you have learned in the previous slide, like you see in here. Because unsigned numbers means they must be positive. On the other hand, if it's a sign and magnitude method and has a leading bit of 1, you need to put the minus sign at front, and from second bit onward, take the bits and treat it as an unsigned number. So the magnitude is taken by the second bit and onward, and the sign is decided by the first bit, so we had put the minus sign. If it was encoded using the ones complement, again you put a minus sign and then you flip all the bits and then treat it as a unsigned number. If it is a two's complement number format, you put the minus sign, flip all the bits, but you add an extra 1 to your result to get the final answer.